Imagine a place in the cosmos where the very fabric of space and time bends and twists. A place where the rules of physics seem to break down. Welcome to black holes, enigmatic cosmic objects that hold secrets deep within their gravitational grasp. At the center of every black hole lies a singularity, a point of infinite density where the laws of physics as we know them no longer apply. It's a place where gravity is so powerful, not even light can escape. But what lies beyond that event horizon? Is there a way out, or does the black hole hold us captive in its mysterious depths forever? And what happens when two infinities collide? Imagine this. You're an astronaut piloting a spacecraft unlike anything humanity has ever built. Its heart, a near-infinite energy warp drive, pushes you to the very brink of the speed of light. As you accelerate, time begins to slow and the energy required grows exponentially, hurtling you toward the edges of Einstein's theory of relativity. Your mission? Something no one has dared attempt before. You're heading straight into the heart of a black hole. At its center lies the singularity, a point of infinite density, where gravity is so intense it bends space-time into nothingness. A place where the very rules of physics break down. But here's the paradox. Your infinite energy warp drive is the ultimate expression of motion and force, defying the universe's limits. The black hole's singularity, however, is the ultimate gravitational trap, pulling in everything, even light, into a realm of nothingness. What happens when your infinite energy meets the infinite gravity of the black hole? Could you pierce through the singularity, unlocking the secrets of what lies beyond? Or would the black hole's overwhelming power drag you into a void where space, time, and energy dissolve into pure chaos? This is the tale of two infinities. Strap in, because this journey into the unknown could rewrite everything we understand about the universe. Black holes are enigmatic predictions of Einstein's theory of general relativity, offer a unique playground for exploring the interplay between classical and quantum physics. Among their many mysteries lies a question that bridges the extremes of physics. What happens when a relativistic particle traveling near the speed of light interacts with the singularity at a black hole's core? Let's consider a semi-classical thought experiment. A relativistic particle begins its journey at a finite distance from the black hole, moving at high speed. As it accelerates under the influence of the black hole's immense gravity, its velocity approaches the speed of light. This raises a fascinating paradox. As the particle's velocity increases, so does its relativistic mass. Meanwhile, the singularity at the center of the black hole represents infinite density, a gravitational force that defies our understanding of physics. What happens when these two infinities collide? In physics, the relativistic mass of an object, denoted as m, grows as the object approaches the speed of light. This relationship is given by the formula where the relativistic mass, m, of an object equals its rest mass, m0 divided by the square root of 1 minus the square of its velocity, divided by the square of the speed of light. Here, m0 is the rest mass, v is the object's velocity, and c is the speed of light. As v approaches c, the denominator shrinks towards zero, causing m, and consequently the particle's energy, to skyrocket toward infinity. This energy is described by Einstein's iconic equation, where the total energy, E, of an object equals the product of its relativistic factor, gamma, its rest mass m0, and the square of the speed of light, c squared. In essence, this equation represents how an object's energy increases with velocity as it approaches the speed of light. In this scenario, the gravitational potential energy of the black hole also becomes significant. The equation for gravitational potential energy near a black hole can be described as follows. U subscript BH represents the gravitational potential energy of the system. G is the gravitational constant, which determines the strength of gravity. M is the mass of the black hole dictating the intensity of its gravitational pull. Gamma is the Lorentz factor, which accounts for relativistic effects as the particle approaches the speed of light. m naught is the particle's rest mass, or its mass when stationary. Re is the distance between the particle and the black hole, with smaller distances resulting in stronger gravitational effects. The equation expresses that the gravitational potential energy is directly proportional to the black hole's mass, the particle's relativistic energy, and inversely proportional to the distance to the black hole. The total energy of the system, which is the rest energy of the black hole plus the relativistic energy of the particle, is equal to the gravitational potential energy of the black hole particle system, expressed as the product of twice the gravitational constant g, the mass of the black hole m, the relativistic mass of the particle, divided by their radial separation, r. But here's the dilemma. This equation pits two infinite values against each other. The first one is the relativistic energy from the particle traveling at light speed, and the second from the gravitational energy from the black hole, centered at the singularity. How can we reconcile these conflicting infinities? Can the particle's energy transform entirely into gravitational potential energy at the singularity? Or does this clash reveal something deeper about the limits of physics itself? In the next chapter of our journey, we'll explore possible resolutions to this cosmic paradox, where the laws of the universe are stretched to their breaking point. To address the infinities in our energy equation, we must challenge the very assumptions that give rise to them. By introducing two groundbreaking axioms, we aim to resolve the paradox of infinite relativistic energy and infinite gravitational density. Our first axiom redefines the nature of the black hole's singularity. We propose that there exists a minimum radius, a fundamental boundary within the gravitational potential. Beyond this point, the compressive force of the singularity cannot operate. This means the singularity cannot collapse into an infinitely dense point. Instead, a lower limit on the radius establishes a floor for how compressed spacetime can become. Our second axiom sets an upper limit on the relativistic kinetic energy of a particle. While the speed of light remains constant, we propose that the energy required to approach it reaches a maximum threshold. This idea modifies Einstein's special theory of relativity for relativistic particles. To unify these principles, we turn to quantum mechanics, introducing the de Broglie wavelength into our calculations. As the coordinate radius of the particle nears the black hole's singularity, it approaches the particle's de Broglie wavelength. This relationship allows us to define the black hole's mass by equating its energy to a formula involving the reduced Planck constant, the speed of light, and the particle's wavelength. Specifically, the mass is expressed as the reduced Planck constant divided by the product of the wavelength and the speed of light. Substituting the minimum radius of the black hole for the wavelength provides a final expression for the black hole's mass. Here, the reduced Planck constant represents the quantum scale, and the minimum radius near the singularity establishes a finite limit. This formulation bridges the gap between relativity and quantum mechanics, replacing the infinite collapse of the singularity with a finite, measurable value. With these axioms, we introduce a framework to constrain the infinities of energy and gravity, replacing them with limits grounded in physical principles. But what are the implications of these ideas? Could they redefine our understanding of black holes, spacetime, and the nature of the universe itself? In the next chapter, we'll explore how these principles open doors to new discoveries, linking the cosmos's largest scales with its smallest and taking us closer to unifying physics. To tackle the singularities that arise at relativistic speeds, particularly the particle's relativistic kinetic energy, we propose a bold modification to Einstein's special theory of relativity. As a particle's velocity approaches the speed of light, c, its relativistic energy, dictated by the Lorentz gamma factor, becomes infinite. But what if this energy had a natural upper limit? What if a particle could transition through the light barrier without encountering an insurmountable singularity? We modify the Lorentz gamma factor by introducing a step function, a mathematical tool that limits the energy of a relativistic particle. The modified energy equation takes the form. Here, beta is the ratio of the particle's velocity to the speed of light, and f of beta is a hyperbolic tangent function. This function smoothly caps the maximum energy a particle can achieve with a parameter sigma called the temporal coefficient, controlling the transition's curvature. The function f beta is given by. This ensures the energy behaves smoothly across three velocity regimes: sublight speeds, where fbb1, near light speeds, where fdv transitions smoothly, and the faster-than-light scenarios, where fv0, providing a framework for hypothetical superluminal particles. Similarly, the Lorentz gamma factor is modified to reflect these changes, ensuring consistent behavior across sublight, light-like, and superluminal velocities. These modifications allow us to regularize the infinities and singularities associated with relativistic motion. By applying these modified equations to our total energy framework, we gain new insights into how particles in spacetime might behave near and beyond the speed of light. Could this step function hold the key to crossing the light speed barrier? Might it open pathways to understanding superluminal travel, or even reveal new physics beyond the limits of Einstein's theories? In the next chapter, we'll explore how these modifications impact our understanding of black hole dynamics and the nature of spacetime itself. With the modifications to special relativity established, we now turn to the interplay between mass energy and gravitational potential. The total energy equation reflects these adjustments, capturing the behavior of particles near relativistic limits. This equation represents the energy relationship in a relativistic context, involving a black hole. It describes the total energy of a system comprising a black hole and a test particle. Here's a breakdown of the equation. The first term, m times c squared, represents the rest energy of the black hole, where m is the mass of the black hole and c is the speed of light. The second term, gamma f times m naught times c squared, represents the relativistic energy of a test particle, where gamma f is the modified Lorentz gamma factor, m naught is the rest mass of the test particle, and c is the speed of light. These two energy terms together equal the total amount of energy for the system. On the right side of the equal sign, we have the gravitational potential energy, which combines several physical quantities: 2 times g times m times gamma f times m naught divided by r, where the variables are defined to be: r is a spatial coordinate, or the radial distance from the black hole, g is the gravitational constant, m is again the black hole's mass. Gamma f and m naught appear again as previously described. This equation balances the total relativistic energy contributions of the black hole and the test particle with a term involving gravitational potential energy. It bridges the rest energy of a system with the gravitational potential of the black hole, incorporating the modified Lorentz gamma factor, gamma f. This substitution is critical, ensuring that our revised framework, which introduces an upper bound on energy, is mathematically consistent with relativistic principles. To delve deeper, we separate the gravitational potential into two components. The first equation is the contribution from the rest energy of the black hole, while the second equation is the contribution from the energy of test particles interacting with the gravitational field. Here we've partitioned the gravitational potential into terms that reflect the distinct roles of the black hole's mass energy and the energy of the test particle. The relativistic energy of the particle, denoted E sub f, uses the modified gamma factor, ensuring a smooth transition across relativistic and superluminal regimes. This energy term directly ties to the gravitational potential, creating two distinct equations for analysis. This term establishes the relationship between the black hole's rest energy and the gravitational potential, anchoring the framework in classical gravitational dynamics. The second term connects the test particle's relativistic energy to the gravitational potential, reflecting how relativistic effects evolve in extreme gravitational fields. By separating these components, we achieve a clearer view of the individual contributions to the total energy equation. This framework lays the groundwork for understanding complex gravitational systems while respecting the constraints of modified relativity. As we refine our understanding of the system's behavior, we begin with the second equation, simplifying it by eliminating the relativistic mass term. This allows us to focus solely on the black hole's mass, enabling us to calculate the minimum radius of the singularity, r, minimum. This radius is a critical value because it is a fundamental lower bound dictated by the de Broglie wavelength, marking the limits of how much matter can be compressed under extreme conditions. From this equation, we can isolate the gravitational potential in terms of the mass of the black hole and the test particle. This equation tells us that the gravitational potential at the minimum radius is determined by the mass of the black hole, setting the stage for understanding the constraints on the radius itself. Now we substitute the de Broglie wavelength, a quantum mechanical phenomenon that describes the wave-like nature of particles at small scales. This substitution provides a clearer path forward in understanding the behavior of matter under extreme gravitational fields. We introduce the Planck constant h-bar and the de Broglie wavelength lambda, tying them to the minimum radius of the singularity. This equation links gravitational constants and quantum mechanics, leading us toward the solution for the smallest radius, r minimum. This is the Planck length, L sub p, which is the smallest measurable length in the universe. It represents the minimum radius to which matter can be compressed under gravitational forces, beyond which classical physics no longer holds, and quantum gravitational effects dominate. Thus, the Planck length serves as a boundary, an inaccessible limit where the classical ideas of space-time and gravity cease to apply, and quantum gravitational effects must be considered. With the Planck length, we've defined a threshold that tells us how the universe behaves at its most fundamental level, where the forces of gravity and quantum mechanics meet. Having established the Planck length as the minimum possible radius in the universe, we can now use this fundamental constant to calculate another crucial value, the Planck mass. By substituting the Planck length into our equations for the test particle, we establish the relationship between these constants, allowing us to solve for the Planck mass. This calculation bridges the gap between length and mass and provides insight into the limits of nature itself at the Planck scale. We begin with the familiar equation for gravitational potential. Now, we eliminate the black hole mass term and solve for the relativistic mass of the test particle, denoted m sub f, which approaches the Planck mass, mp. We now have the relationship that reveals the Planck mass, mp, as a function of the Planck length and the gravitational constant. This mass represents the upper limit on how much mass a particle can possess, an essential constraint in the universe's most extreme environments. This equation defines the Planck mass, mp, as the square root of a ratio of fundamental constants. It represents the fundamental limit of mass and encapsulates the intersection of quantum mechanics and gravity. This equation illustrates the connection between the relativistic mass and the Planck mass, showing that the maximum mass a particle can attain occurs when its velocity approaches the speed of light, where the warp factor beta approaches 1. At this point, the particle's relativistic mass is capped at a large value, no longer able to grow infinitely. This behavior is encoded in the modified Lorentz factor, which uses a transition function to limit mass and energy as a particle approaches the speed of light. By introducing the temporal coefficient sigma d, we establish an upper bound for relativistic mass. If sigma d is relatively large, it approximates the standard coefficient sigma. This step ensures that as a particle's velocity approaches light speed, the mass or relativistic energy reaches a maximum value, rather than continuing to increase without bound. This relationship ties the temporal coefficient to the ratio of the Planck mass and the rest mass of the particle, revealing how the limiting factor for relativistic mass is inherently tied to the fundamental constants of the universe. Thus, the Planck mass represents the maximum mass a particle can achieve, and the Planck length sets the minimum size of matter. Together, they define the fundamental limits of our universe. These constraints prevent the unbounded growth of mass and energy, ensuring that the laws of physics remain consistent even in the extreme environments of black holes, or at relativistic speeds and beyond. In our thought experiment, we began with a relativistic particle falling into a black hole, exploring its interaction with the singularity. The equations we derived offer profound insights into the limits of our universe under extreme conditions. Let's take a moment to review the key equations that have shaped our understanding. We began by equating the total energy of the system to the potential energy of the black hole itself. This foundational equation helped us establish the relationship between the relativistic energy of the particle and the energy of the black hole. Next, we accounted for the energies involved, the rest energy of the black hole and the energy of the particle falling in. This simple equation sets the stage for understanding how mass and energy balance out in the face of gravity's pull. We then modified the relativistic energy of the particle, ensuring it could become large but not infinite. To achieve this, we introduced a step function, a transition function, that smooths out the energy behavior of a particle traveling at light speeds. This function allowed us to describe particles moving at relativistic velocities, capping their energy to avoid an unbounded growth. The step function itself is a key ingredient in our model. It represents the curvature of spacetime as particles approach the speed of light, allowing them to transition into tachyonic particle states. The function defines the limits of energy growth as the particle nears this critical threshold. This equation connects the temporal coefficient to the Planck mass. It gives us a clear measure of the temporal curvature as the particle moves toward relativistic speeds. The temporal coefficient governs the bending of spacetime, with its value revealing the maximum possible energy a particle can attain. This modified Lorentz gamma factor uses a step function to control how relativistic effects grow as an object's speed approaches the speed of light. Instead of becoming infinite, as in the standard case, the step function ensures the values remain finite. This approach is useful in theoretical models that need to manage extreme speeds or energies, such as those found in intense gravitational or relativistic environments. Using the metric of a black hole, we derived the gravitational potential energy. This equation connects the mass of the particle, the gravitational constant, and the distance from the black hole, essential for describing the energy exchanges during the particle's descent. As the particle approaches the singularity, we invoke the de Broglie wavelength and set it equal to the coordinate length. This relationship allowed us to derive the minimum radius, a key step in defining the Planck length, the lower bound of compression for matter under gravitational forces. The Planck mass is a fundamental unit of mass in physics, representing the scale at which quantum mechanics and gravity converge. It is incredibly small compared to everyday objects, but massive relative to subatomic particles. At this scale, the effects of both quantum fluctuations and spacetime curvature become significant, making it a critical value for understanding phenomena like black holes, the early universe, and the unification of fundamental forces. By combining these equations, we've addressed the paradox of infinities that arises in black hole physics. Through careful incorporation of an upper bound on relativistic energy and a lower bound on radius, we've established a more consistent framework, one that accounts for the limits of energy, mass, and size in our universe. These equations provide a clearer, more complete interpretation of the behavior of particles under extreme gravitational conditions. In the end, these equations offer us a deeper understanding of the very limits of nature. Through the Planck scale, we touch upon the very edges of what is physically possible, resolving the infinities once thought to be insurmountable. A particle racing toward a black hole, but not just any black hole. This one is extreme, and it's about to reveal a fascinating possibility. Could particles traveling near the event horizon of a black hole break the speed of light? As we dive into this scenario, we're looking at the interaction between two powerful forces, relativistic motion and the immense gravitational field of a black hole. This is a place where the normal rules of physics are tested to their limits. To understand this, we first need to establish an equation for energy conservation. Before and after the particle interacts with the black hole's gravity, its total energy must remain constant. But what happens when this interaction involves speeds close to the speed of light? Let's break this down. The initial energy of the particle includes its kinetic energy, how fast it's moving, and its gravitational potential, which depends on how far it is from the black hole. As the particle gets closer, this potential increases and the speed also ramps up. Here we express the energy conservation with this equation. We're looking at the balance between the particle's energy and the black hole's gravitational pull. But things get interesting when we calculate what happens at the particle's closest approach. At this critical point, we consider the gravitational potential and relativistic mass to be roughly constant, simplifying our equation. By manipulating these terms, we see something extraordinary unfold. As the particle approaches the event horizon, its energy and momentum behave in surprising ways. This equation shows how the influence of the black hole's curvature changes the particle's velocity and energy distribution, making it possible, under specific conditions, for the particle to overcome the light barrier. Next, we will consider two cases to understand the physics. Case 1, the test particle is far from the black hole. Here we analyze a particle far from a black hole, where gravity's impact is minimal. The modified Lorentz factor simplifies the ratio of relativistic mass to rest mass as the particle approaches light speed. With R2 at infinity, the gravitational potential fades, resembling free space conditions. At this distance, the gravitational potential term approaches zero. Now here's where things get really intriguing. When the particle nears the event horizon, the space-time around the black hole gets warped more intensely. The closer the particle gets, the easier it becomes to surpass the speed of light. In the far-off distance, this effect is small. But as we approach the black hole, things change dramatically. The equation tells us that as the particle gets closer, its velocity can increase so rapidly that it might exceed the speed of light, something that Einstein's theory of relativity tells us should be impossible. Now we examine case 2, where the particle near the event horizon of a black hole, where gravitational effects dominate. As the particle approaches the speed of light, the modified Lorentz factor converges to sigma, simplifying to the ratio of relativistic mass mp to rest mass m naught. Near the event horizon, where R2 approaches r naught, the closest approach, the gravitational potential term approaches a critical threshold, revealing the intense influence of the black hole's curvature on the particle's motion. The key here is the temporal coefficient, a factor that describes how time behaves under extreme gravity. As this coefficient decreases near the black hole, the energy required to reach relativistic speeds lessens. This creates an environment where superluminal speeds might just be within reach. This idea challenges everything we know about the nature of black holes and the speed of light. If particles are near the event horizon, extreme curvature may make it possible to reach faster than light speeds. We may be on the verge of rewriting the rules of physics. This thought experiment invites us to rethink the boundaries of relativity and opens up a whole new world of possibilities in the universe's most extreme environments. As we continue to push the limits of physics, we may find that the impossible is not so far out of reach. Stay tuned as we explore even more mind-bending possibilities in the next section of our journey. I hope you enjoyed this program. Please show your support for my channel by clicking that like and subscribe button. You can also order my book, Tachyon Drive, Faster Than Light Travel Within Special and General Relativity. This book is your gateway to an exhilarating journey into the cutting edge of theoretical science. This groundbreaking collection of ideas extends the genius of Einstein's theories, unveiling bold solutions for breaking the cosmic speed limit. By delving into the very fabric of spacetime, Tachyon Drive explores how tachyon particles, hypothetical entities that exist beyond the speed of light, could become the cornerstone of interstellar propulsion. Imagine a beam of these particles, propelling spacecraft to traverse the vast cosmos at speeds we've only dared to imagine. Tachyon Drive, Faster Than Light. Travel Within Special and General Relativity, available now on Kindle. Join the journey beyond the speed of light and into the future of exploration. Link in the description below.